Okay, so I said in a previous video that anytime we had a measurement, we had to talk about the number part and the unit part, and then we talked about units. We talked about unit conversions, we talked about the empirical system, the metric system. What we need to talk about now is the number part. And the problem with chemistry is that the number part gets really, really tedious. And we use these things called significant figures. And what this does is this keeps track of the accuracy of measurements. And honestly, most of the time, that isn't a big deal unless you're doing calculations. So I'm going to add during calculations. In labs, we measure things all the time and we multiply numbers together, divide numbers together all the time. So being able to keep track of how accurately you measured something is really, really important. Okay, so I'm going to do an example. This is going to be a very rough sketch. I do not need you to reproduce this perfectly on your notes. Okay, this is supposed to be a ruler. It is not going to be to scale, but honestly, it's probably not too far off since I'm doing it on paper and blowing it up for a YouTube video. Okay, we're going to give it units of centimeters because metric system. I don't know. Kind of eyeballing this right now. If I had a real ruler, I'd probably try a little harder. Okay, so 1, 2, 3, and 4, and then most rulers that you'll ever use in your life are there's a division of 10 in between each of these. So I'm going to cut it in half. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Not perfect, but it's good enough for what we're doing. Okay. So what I'm going to do is I'm going to draw a line, and we're going to talk about how to measure this. This sounds really anal retentive, and I'm sorry. Okay. So when we're measuring things, we want to be as accurate as possible. We want to get as many decimals as we can, but every piece of equipment that we use is limiting. We can only measure so accurately. Okay. So if we glanced at this, we're assuming this is at the end. I don't know if I drew it real well, but we'll assume it is. This end, it's somewhere between 2 and 3. So it's 2 point something. Okay. Now, these are tenths, so that's 0.5, so 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. If I'm eyeballing it, it looks like it's between the 0.5 and the 0.6, so it's 0.5 something. There aren't more lines in between there, so we can't, with the amount of certainty we have on this last number is dropping pretty quick, but we know it's 2.5 something. Okay, and if I look at it, it looks like it goes just shy of halfway. So I'm going to say it's 2.54, which is pure coincidence that that's literally 1 inch. 2.54 is 1 inch. I just drew a line. So anyway, the problem is, in terms of interpreting this, we're not even sure about this number. We certainly can't get another decimal. So we've hit the limit of how accurately this instrument measures things. And so it is understood when you talk about measurements that the last digit is uncertain. We still record it to the best of our ability, but it's going to have some fluctuation in it. So if somebody else came along and measured this, they might say, oh, it's 2.3 or 2.5. So whenever you see a measurement written down, you are supposed to interpret it as the last number being plus or minus 1. So this number is somewhere between 2.53 centimeters and 2.55. I measured it as 2.54. Somebody else might measure it as one of those other ones, but it's going to be somewhere in that range. This is also true of digital instruments. So if you use a balance in the lab, and it says 19.743 grams, you are supposed to interpret this as being 19.742, somewhere between 19.742 and 19.744. Okay, it's understood that that last digit is plus or minus 1. Okay, Now, what we want to know is how do you keep track of this during calculations? Well, we're kind of putting the cart before the horse. We need to figure out what this is. Significant figures, I will almost never call them that again. They are typically abbreviated as Sig Figs. Occasionally, you have textbooks or instructors that call them significant digits, Sig Digs, but honestly, about 99% of the population calls them Sig Figs, so that's what I'm going to teach you. Okay. Keeping track of Sig Figs is tedious, but unfortunately, it's kind of one of those things we have to do it anytime we see math in this class. So, let's try a couple examples, kind of learn the rules, see how it goes. Okay, so these are the Sig Fig rules, I guess. So the idea is all non-zero digits are Sig Figs. Okay, and if something isn't a Sig Fig, that doesn't mean that we can ignore it. It just means that it doesn't count towards the accuracy of the measurement. Okay, so if you see a 1, 2, 3, 4, 5, 6, 7, 8, or 9, count it as a Sig Fig. Okay, this means that zeros are the problem. I don't know if that E is supposed to be there, but probably not. Zeros. Okay, so with zeros, it kind of depends. It's a lot of if-then statements. So if the 0 is between two non-zero digits, then it counts as a Sig Fig. So for example, if we had 17.0456. Okay. The 1, the 7, the 4, the 5, and the 6 are all non-zero digits. They're all Sig Figs. Okay. This 0 is in between two other digits, two non-zero digits, so it counts also. So this number would have 1, 2, 3, 4, 5, 6 Sig Figs. Not too tough, right? Honestly, you're just counting how many numbers are in a number. It sounds repetitive and tedious. Sorry. Okay. As far as zeros, they can either be on the left side of the number or the right side of the number. Okay. So, if the 0 is on the left, which are sometimes called leading zeros, they do not count as Sig Figs. So, for example, if you had 0.00413, and we want to know how many Sig Figs there are, we know the 4, the 1, and the 3 definitely count. The zeros on the left are not considered Sig Figs, so this would only have 3. Okay? So zeros on the left do not count. One way to think through this is if you put it in scientific notation, which I'm kind of running on the assumption you've heard of scientific notation and know how to do this. Essentially, you make sure this number is between 1 and 10, and then put a decimal and then the rest of the number. So it'd be 4.13 times 10 to the, it would be 123 times 10 to the negative third. You can put this exact same number in scientific notation and the zeros disappear. That doesn't mean they're not important. It is, you're not going to get the same answer if you put 4.13 in your calculator as if you put 0.4 or 0.00413. But it just means they're holding the decimal place. They're not important otherwise. Okay? If the 0 is on the right, it kind of depends, honestly. They count as Sig Figs as long as there is a decimal. So if there's a decimal point anywhere in the number, they count as sig figs. So for example, if you had 20.100, okay, the 2 counts, the 1 counts. This is one of these previous rules where it's in between two non-zero digits, so that counts. There is a decimal point. These are on the right, so they count also. So this would have, this would have 5 sig figs. Okay. The other way to think through it is if we compared this to 20.1, this would only have 3 sig figs. Sorry, I'm switching pens and messing this up. This number should be interpreted as being between 20.099 and 20.101. This number should be as being interpreted between 20.0 and 20.2, which is a much wider range. Okay, so these zeros are definitely causing an impact on how we interpret the number. Okay. If there's a 0 on the right, if there is no decimal, it's really unclear. Okay. So let me show you a couple examples to show you what I mean here. So an example of one that is unclear because there's no decimal is, for example, suppose you were typing in your calculator and you did some measurements and you multiplied some things together and you got a number, and your calculator, which doesn't know what a sig fig is, spit out the number 4,000. Okay, and we haven't learned the rules about how to know how many sig figs to keep based off what your calculator says, but let's say you need to have 3 sig figs or 2 sig figs. How do we know? The problem is this is inherently very, very, very unclear. So if we wanted, let's say 2 sig figs, say our calculator spit it out and we know that the answer is supposed to have 2 sig figs, there's a couple different ways to do it. The most tedious, but probably the most accurate, is to put it in scientific notation, because it'll introduce a decimal. 4.0, now that there's a decimal, this is 2 sig figs. And this is 3 spaces away from the 0 spot, so times 10 to the positive third. Okay, this would have 2 sig figs. I'm gonna keep writing it in red, keep my notes consistent if possible. Okay, I tend to not do this. This is correct, and if you see scientific notation, this is the easiest way to do it. Well, it's the easiest way to interpret it because it's clear. It's a pain to write it though, and most people don't cycle back and forth between scientific notation and regular writing easily. So another way to do it, and I went through 6 years of chemistry at Eastern Illinois University. I'm originally from Illinois, and I only had one professor who ever had a problem with this, and it was a semester-long class, basically about statistics and sig figs. The easiest answer is to just literally put a line over the last sig fig. So I know this means repeating decimal, but there's no conflict of interest because you never have repeating decimals on measurements. It has to stop somewhere. So that's why we use it, is there isn't a conflict. Okay. This indicates the last sig fig, and anything that comes after it is not considered a sig fig. So these 2 are sig figs, this is not. Doesn't mean they vanish, it's still 4,000. It's not like it drops down to 40, but yeah. This is what I typically do. This is my preferred option here. This is what I recommend. If you write this in your labs, in other classes, people will know what you're talking about. Okay. My professor who had problems with this in college taught us to do it this way. I hate this method, and I in no way, shape, or form recommend it. Essentially, anything that isn't a sig fig, you keep them, but you write it as a subscript. It's useful when you're typing, but it's a pain to do. So this would still mean 2 sig figs. I know from experience my students' handwriting is pretty inconsistent, and I can't guarantee that I could read what the difference is here. So this is an option. I highly, highly recommend the second one. Basically, plan on seeing that a lot. Okay. All right. A couple other nitpicky things about sig figs. So I think we had 1 and then 2. 2 is all about zeros. So now we're on 3, I guess. Unit conversions are assumed to have unlimited sig figs. So what that means for us is so for example, when we say 1 foot equals 12 inches, we are not assuming this is 1 sig fig and this is 2. We're assuming, write it in a different color, I guess. We're assuming that 1.000000 whatever to infinity feet equals 12.000000 inches. And so basically what it means is anytime you're doing a calculation, your unit conversions are never going to limit your sig figs. Okay? Anytime you use physical constants, just keep enough sig figs to not limit your answer. Okay, so for example, if you have pi, this can be written as 3.14. But if you had a calculation that's going to have like 6 sig figs, this would limit the accuracy of all your measurements when you're doing calculations. So just basically it's almost easier to hit the pi button on your calculator or insert the symbol pi. So 3.14159265359, I think. I don't know. It's been a while since I learned that. But anyway, the idea is you don't have to put every number in because obviously this goes on to infinity, but put enough that it doesn't limit your answer. Okay. There are other constants that we're going to see throughout the semester. Just same idea. Anytime you see a constant, don't let it limit your answer. Okay. All right. We'll continue sig figs in the next video. Thank you.